Okay, here's the solution for Quiz 4, Spring 2017 MSE201. This problem wasn't particularly challenging. I wanted it to be something that it was really more of a test of if you'd been working on the homework, and I know the last two quizzes the scores were a little bit lower, so I think that I might have been asking questions that had a little bit too much involvement for the time in class. So I thought I'd make this a little bit shorter. Let's look at this. Basically where I'm saying, asking you to use the table below to determine the diffusion coefficient for magnesium and aluminum at a given temperature. So this is something that you should automatically be able to tell that we are going to be using this Arrhenius relationship for the diffusion coefficient. So just write that down now. D equals D0 exp of negative QD over RT. Why R? We're using R because our units are joule per mole for the activation energy. If the activation energy were in joule per atom or joule per hop or per event, then instead of R, we would be using K, the Boltzmann constant. Remember, the only difference between the Boltzmann constant and the gas constant are the units, where the Boltzmann constant is joule per atom per K or EV per atom per K. The gas constant is energy per mole per K. So you can relate the two by Avogadro's number if you need to do that. There. But for this problem, we don't need to. The next thing to point out is that looking at these, there's data for interstitial diffusion, data for self-diffusion, and data for interdiffusion. And in particular, this has the word vacancy in parentheses. So this is interdiffusion of one diffusing species into a host species, given that vacancies are assisting in the process. So if you remember from class, I said you could have direct exchange of atoms switching places with each other. You can have vacancy assisted, and you can also have interstitial assisted. But for metals, and that's the data set we have here, really it is vacancies that are the primary means for assisting the diffusion process. So this problem really is a matter of just being able to read the data, recognizing that we want to look for magnesium in aluminum. We are looking for this data. Which means that we get D is equal to 1.2 times 10 to the minus 4 exp of negative 130,000 divided by R, which in the proper units of joule per mole per K is 8.314, and T. And in this case, because this is joule per mole K, T has to be in Kelvin as well. So 550 plus 273 gives us 823. 823. Remember, the exponential, in the exponential, the resulting units have to be dimensionless. So you want to take the exponential of a unitless number. And our final diffusion coefficient is going to be in units of meters squared per second. And if you need to transform that, of course, you can. Putting this into the calculator, we get 6 point, excuse me, 6.73 times 10 to the minus 13 meters squared per second. And that is the solution for quiz 4.